just to give you, some recap on what we did last time. So Six Sigma is basically a 12-step process apart from the define. So as you can see the slide, the first three, which is A, B, C, which is your define step. And we went through how to identify the project CTQs, and we developed a team charter, and we defined process map. And then we selected the CTQ characteristics using a fishbone analysis. And then we did define performance standards. We defined what Y should be. And that's where we are. And we also did a little bit of view on basic stats, where you understood the average, central tendency, as well as variation.
Yes.
Okay, so I hope you still have an idea on what we discussed in detail on each of these categories.
Sure.
Right, okay. Yeah, so today we will move on to the third step in measure, which is measurement system analysis. So this is a very critical step. Before we even go ahead and collect the data, we need to ensure the measurement system is accurate. And that's what we will learn. And we will also do a couple of exercises on Minitab. And the next step, we will quickly jump into the analyze and look at the process capability, and how do we establish a process capability using statistics. We will also go through some sample data in detail to understand the distribution, the shape of distribution, as well as the stability of the data. And analyze in detail, probably we will keep it for the next session, because that's a little more detail that we'll have to get into. So that's where we will close for today.
Okay, so basically we're going to do measure today.
Yeah, measure, third step of measure. The first two is kind of we've covered.
Yeah.
Right, and we looked at the data collection plan as well, and how do we keep the people who are helping you to collect the data. And we went through that, and we will get into the MSA right now, measurement system analysis.
Okay.
Okay. All right. Now, you understand a process variation, right? So it is a spread from the central tendency, is what we consider as the total variation. So there is something called observed process variation, which is a total variation in a process, right? And which includes the actual process variation and a measurement variation. Okay, so let me give you an example. So let's say this is the distribution of the data that we have, right? And this point is the central point, right? And this could be your lower specification limit, and this is your upper specification limit.
I'm still seeing. I don't think I'm seeing what you're seeing.
Okay. Let me just check.
Oh, what the fuck? Wow. I'm seeing, what I see right now on my screen is 12-step Six Sigma process.
Okay. Yeah. Let me just.
I continue to see the same. Okay, now I see a different, yeah.
Right. So let's just say this is the distribution of a data that we are measuring.
Yeah.
And you have the central tendency right here, right?
Yeah, central tendency is normal distribution.
Right, absolutely, yeah. So you have the lower specification limit here given by the customer, and you have the upper specification right here.
Yes.
The data is very much showing within the specification limit, which means the process is looking good. And this is your central tendency, right?
Yes.
And this part to this part is the total variation that you have.
Yes.
Right now. So the total variation is the distance from here to here, or from here to here. That's what it says. Now that is called the observed variation. That's the total variation in a process. Now, this variation can be caused due to two factors. One is your regular predictable process variation, which occurs on a regular basis. And the second could be a measurement system variation. The way in which we measured a particular metric could be wrong. A measurement equipment that we've used, a gauge that we've used, has an error, or the operators who's trying to help you to collect the data could be wrong, right? Now, let me show you that in detail. Right? So the total observed variation could be due to two reasons. One is actual process variation, and the second is measurement variation, right? In the measurement variation, there will be two main kind of variation. One is variation due to the gauge, right? For example, if you're asking a person, an operator, to collect the data using the same equipment and measure the same part over a period for at least 2 or 3 times, right, minimum, or repeated time, and if the readings are different, right, and that is called variation due to gauge.
Right. It's either, so basically it's either variation, right? Variation due to gauge is either the instrument, the device, the tool that's being used to measure is off. And then the other one, variation due to operators, is perhaps the person, the human, that's not performing the task properly.
Absolutely, yeah. So the first one, the gauge variation, we call it as repeatability. And variation due to operators, we call it as reproducibility, which means 2 different person or 3 different operators unable to give us the same result because of some of the other issue with the operator, and that is called reproducibility. Okay. And calibration is something, if the gauge has a calibration issue, for example, if we are trying to adjust different units within the gauge to adjust and get the readings that we require, and if the gauge is not able to produce that, that is called a calibration issue. And stability is something over a period of time, we are trying to measure the same metric, and if we get different results, and that is called stability. And linearity is again very similar to calibration. For example, if you're trying to measure 2 different sizes of a part number or 2 different kind of part number, and gauge is unable to give us the same amount of results as it is. So all these put together is called the gauge variation. Right now, let me show you a little more detail. Can you see the new slide now?
Yes.
Okay. Now, again, here observed variation. The first one is unit to unit variation. It's either called unit to unit variation, a true variation, or a process variation, or it could be a part variation. Second one is measurement system error, right? Which is precision related, which is repeatability or reproducibility, like I just already mentioned. Stability is a measuring error which happens over a period of time. Bias is the distance from the mean to the total variation. And linearity is anything to do with gauge capability to measure different sizes, right? Let me show you some examples. For example, this is the distribution that we are talking about. And this is the upper specification limit, right? And if one measurement several times, if he does the appraisal, And if the results are different, then it is called a repeatability issue. Reproducibility issue, there are two different operators, two different distributions, and you get two different results. An average of this one is different from the operator X, and this would be called a reproducibility issue. Right. Now, there are a few more concepts that you'll have to understand. One is accuracy. Accuracy, which means you're hitting the target, you are reaching the average of the standard, even though your distributions are around the target. That's called accuracy. Precision may not be hitting the target, but you're hitting at the same point all the time. And precision and accuracy would be something what you see here, which is hitting the target consistently, right? And this one is off the target as well as it is not consistent. In majority of the cases, if we are pulling a data from the system, we should ideally be getting this, unless the operator makes an error by not recording the right or not pulling the right kind of report, or not selecting the right parameters to pull that kind of a report. And bias is something which is away from the target. Let's say 3 different operators here, and the first one getting here, second one gets this as the central tendency, and third one gets this as the central tendency. So the difference from here to here is bias, the distance. Stability, like we discussed, it's a variation which happens over a period of time. And linearity, an example is, does my gauge have the same accuracy for all sizes of objects being measured? Okay. Now, MSI fall into 2 categories. One is attribute and one is variable. Right? And this is something we've already discussed. Anything which is attribute or discrete is called pass or fail, go or no go, the number of defects, this kind of measurements. Variable is anything that we measure on a continuous scale. So there are 2 different tests that we would be using for each scenario. For attribute kind of a data, we would be measuring it in a different way. And for continuous data, we would be measuring it in a different way. Now, let me show you an example. In Minitab, how are we going to calculate the measurement system variation? Now, let's say this is the data that we have. So what we've done is we took a sample of data points to check if there is a measurement system variation is available or not. So the key objective of understanding the measurement system variation is, from the total variation, we are trying to reduce anything that is related to the measurement system. And we only have process variation, which is the true variation, which should be analyzed for our further project and identify solutions, right? And that's how we try to eliminate. For example, if there is an issue with the gauge, we can always go ahead and change the gauge. If it is too expensive to change the gauge, we can always change readings, which can give us consistent results. That is one. If we are getting issues from the operator side, we can always go back and retrain the operators who collects the data, or we could look at changing the operator who can give us a better data. Which means that from total variation, one key factor of measurement system can be eliminated, and we focus only on the process variation, or measurement system error can be minimized. Right now, this particular data set, I hope you can see this. Are you seeing a Minitab screen?
No, I only see I see the slide with the attribute and variable variation. Okay, now I see it.
Just check when I skip my pages. Let me check if there's a setting that I can use. That's fine. Right. So this is a Minitab. Have you used a Minitab before?
Oh, a Minitab? No.
Okay. I request you to download the Minitab trial version so that
Okay.
when we proceed, we could, you can also do a trial from your end so that you understand this tool better.
Well, what is this, like Excel?
Yeah. So if you go to Google and type for Minitab, have the access to download the software, you get a trial version for 30 days.
Okay.
Would
Well,
you want to give it a try in the background when we explain?
yeah, what's the what is it?
Version 18 Minitab.
I have so you want me to download it on the computer or cell phone?
Yes. If you have the right to download on your computer, will you be able to do that?
No.
Okay, that's fine. Then you can watch my screen when I explain.
Okay.
See if you could download it for tomorrow and we can do some testing or practice. All right, so this is how the tool looks. So you have, this is a statistical analytics tool, which is mainly used for Six Sigma projects. So you have, it's kind of similar to Excel, but it is a software which can give us results, right? For example, if I look at the statistics, you have multiple analytics, which is already built into this particular tool, right? If I want to get basic statistics on mean, median, standard deviation, if I want to calculate anything, and if I want to showcase that in a graphical way of distribution, I could use this tool. There are different uses which we'll get into. The first one is we are looking at measurement system variation for a attribute kind of a data or discrete data. So if you look at this database, so the first column is SME, right? Which means that the subject matter expert of this process has taken about 30 samples of, or let's say 30 part numbers, right? And he's given his reading whether the part has met a metric or not. Let's say if this is the on-time delivery, what does this indicate is the first part number is a pass, which means that it is met the on-time delivery, right? So similarly, is done a pass fail against each of those part numbers. There are 30 part numbers, right? And he asks, and this is a standard, right? This is something an SME helped us to do it, or we pulled it out from the system. And for data collection, we are asking 3 appraisers to do 2 trials each. So the first one, appraiser does 1 trial, and appraiser 1 does again another trial. The appraiser 2 similarly does 2 trials. Appraiser 3 does 2 trials. Now we have got 3 appraisers doing 2 trials each for 30 different part numbers. And the data is plotted in this particular format. This is what we will use for an attribute gauge MSA test. Is that clear? Any questions here, Ronald?
No, that's clear.
So then we go to Stat, Quality Tools, and then we click on Attribute Human Analysis. And since we have multiple columns that we are analyzing, we click on the multiple columns here, and we select from the top. Okay, we select all the appraisers first, then select. Okay. Now I input saying that there are 3 appraisers and there are 2 trials, and I also click here and select the SME. And you can also put a price and names if you want a customized result. And this is how it look. Any questions here?
Okay.
Good to go. All right, then I click on OK. And this is how I get a result. Now the first one, it shows within a prices, 3 different data, right? And here it shows a pricer versus standard. Now let me get into the details and explain what it actually means. Now the results are showing up right here. Start from the beginning. Now a price of 1, he's inspected 30, it matched 30 and it shows 100%, right? Now I will, now let's see. And
but how is that so? Because if you look at line item 6 on the Excel, on the workbook, you see that the SME says fail, but appraiser 1 is claiming pass.
right, absolutely. So you're going to see that right now. So now this is a tab to look for accuracy. So now what you're talking about is accuracy, right? The SME says fail and the appraiser all say pass, which means there's an accuracy issue on this particular part number, right? Now, each appraiser versus standard. Standard is nothing but what SME is given, right?
Yeah.
Now, the first one, if you look at, he's inspected 30 and match is 28 and 93% accuracy.
Sure.
Second one is 96 and the third one is 80.
Sure.
Right. So exactly what we saw in the graph, there is a there's an issue with the third appraiser in terms of accuracy. Now we will see further results. Now what we've seen is only accuracy, which is appraiser versus a standard. Now we'll have to look at repeatability as well as reproducibility, right? Two other metrics. Now between appraisers, which is nothing but your reproducibility, which is only 80%, right? And the minimum criteria to pass reproducibility is 90%. That's what we usually set in doing a project in a service industry kind of an area, right? And then we also analyze all our prices versus standard. Again, you get a percentage of 76%. And this is the detailed analysis of each of those, right? So 2-3 different factors analyzed here within appraisers, appraiser versus standard, and the trials within appraisers. What is the total? So we will get to know which appraiser has an issue or if there is any repeatability issue with the gauge, or if there's any accuracy issue that we are facing against the standard measurement that has come through. And based on this, we will be able to fix if there's a problem with the measurement system. Clear?
Sure.
Okay. Now let's look at another set of data, which is the continuous data. Okay. Now here what we've done is, let me show you a thing. Can you see the new sheet?
Yep.
Here again, we have taken about 10 part numbers and 3 operators. doing 2 trials, and this is how we plot for a continuous data, and the reading comes something like this because it's on a continuous scale, right? And we go to stat, quality tools, go to gauge study, and we select the nested gauge R&R study because you have multiple part numbers. Okay, now click on the first one. It clearly says part or part batch number. You double click on the part. Operators, you double click. Measurement data, which is nothing but the reading. And options. Click on OK. You get a graph something like this. So if you look at the first one, there are 4 columns, right? First is gauge R&R, which tells you the total measurement system variation, right? Right. Yeah. Now comparing this, there are 3 different readings, right? One is gauge R&R, which is the total variation. So you get this one, and then you have repeatability, which is your gauge error. Reproducibility is within prices, and then you have the part-to-part variation. This is the actual variation, right? Now, total gauge is showing 3.17. So around 12% variation in the 12% is contributed in the total gauge R&R. Repeatability again 12%, reproducibility absolutely 0, and part-to-part variation is 39%. So the total variation is showing us 40%. Right now, there are 3 categories that we look at when we assess in the industry standard how to read this particular data. The first one, study of variation, right? If the study of variation is anywhere between 0 to 10%, the gauge is acceptable, right? Now let's see. Which is 3%. Right? This is in the acceptable range. Repeatability, again, it's showing 3.1%. Okay. And fourth category is distinct category, which is showing us 7. Acceptable range is 5 to 10. 5 to 10 is something maybe acceptable based on the application and cost, and anything above 10 is acceptable completely, right? So what does it mean is distinct category. So there are 10 different part numbers here, right? If the distinct categories, if you get it as 1, which says that the system cannot really differentiate between part numbers, which means that all the 10 part numbers, from the total 10 part numbers, we're getting only 1 distinct category, which means that this data is not good to identify measurement system analysis. You'll probably have to change the part numbers or select a different set of data. So here we have 7 categories, which means that the system is able to differentiate between the part numbers, and there is a part-to-part variation, which is clearly evident. That's what it happens in a distinct category. So once you do this test, look at these three factors. One is study variation mainly. Tolerance is something we set. Contribution and distinct categories. If it comes into these three gauge, which is in either in the yellow or the green zone, the gauge is acceptable. Or we'll have to change the data, or we have to look at reproducibility issue or gauge issue. Are you clear on any questions here?
Yeah, you basically it's just a report measuring amount of human or operator with parts and different types of application or job or operation that the operator will be performing, and getting a recording any variation from the target, and let's say just generating the percentage and the read.
Right. Okay, so the main objective of doing this test is
To have consistency, to identify whether it's the tool, the measurement tool or equipment that you're using that is off, or it's the actual operator, the human.
right, and minimize the measurement variation completely as less as possible. At least
Right.
keep it in the acceptable range of variation that can happen, because you obviously may not be able to change the gauge because there could be a cost of replacement, or you wouldn't be able to replace an employee because of certain reason. We at least can go ahead and train the operator who can give us a better measurement, basically,
Right.
right?
So yeah, basically just basically just gathering data, collecting data, measuring it, and analyzing it, and then you make a determination whether it's after you analyze the data, whether it's human error or like the operator, or it's a measurement tool. And then from there, you make, do your action plan accordingly. If it's like you said, if it's an operator, then you provide better training. You improve on your training for the operator, or you identify what is the root cause of the operator having so many discrepancies or having so many variations. Or if it's the tool, like you mentioned, either you replace it or you recalibrate the tool, or or you keep using the same tool, but you maybe, I don't know, do some maintenance on the tools or equipment.
Right. Perfect. Now, an example on how it turns out to be. Let's say this was the total variation before, right? And when we minimized the measurement system, without the measurement system variation, the process would become a little more leaner, which is a better data for you to go ahead and start analyzing.
The true value is the better data because you're closer to your central tendency.
Right.
Your variation limits, your upper and lower are much more reduced and closer to your central tendency.
Right. Perfect. So the total variation contains two things. One is part variation, and then you have the measurement variation. So measurement variation, if you further break down, you have reproducibility and repeatability, right? Which could also be an operator versus variance or operator versus part variance.
Mm-hmm.
This is something we've already seen. This is basically the calculation, how it works. Right. So if you had the Minitab today, I could have given you an exercise of 10, 15 part numbers, and you do the analysis by yourself and see if it fails or not.
Hello? Hello.
One moment, yeah.
Okay.
And this is the format at which we do the test and how we collect the data. All right. Now we'll move on to something called process capability now. So what we have learned is from the 12-step process. So we have almost covered the measure phase. And just before we move on to the analyze phase, we would like to estimate the capability of the process, right? If you remember initially what I was talking was, first you have a practical problem, and then you convert that practical problem into a statistical problem, and you identify the root causes and come up with a statistical solution, and then you convert that into a statistical practical solution, right? Now we are measuring the data, and the next step is for us to study the capability of process through statistics. And that's what we will do in a process capability study.
Can you go back to the, yeah, 1 second. Can you go back to the measure?
Now in process capability, what we usually find out is whether the process has the capability to meet customer expectations or not, right? And we put a measure to it with a number, which I will show you in some time. And we look at the specification limit given by the customer, and we check, are we meeting his expectation or her expectation? And we put a measure to the process capability, and we set a benchmark from then with a target to meet the customer specification limit. That's what we do in a process capability and benchmarking study. Now, to give you an example, if you look at this particular chart, let me pull out another example for you, which is a little more easy to understand.
Okay.
Yeah, so this is something we've already seen before, right? This is the central point, and distribution is from here to here. And this is the specification limit given by the customer.
Yeah.
Right?
Yes.
And if we have to plot 3 sigma from central point towards your upper specification limit, let's say 1, 2, and 3 sigma, right?
I'm sorry, can you repeat that?
For example, this is central tendency, right?
Yes. Yes, the variation is between plus or minus 3.
Yeah, plus or minus 3 if you plot the variation. So let's say it comes to this point, plus 3, and this side plus 3. So we have a total of 6 sigma, right?
Yes.
The assumption is if we have 6 sigma plotted from the central tendency, it would capture almost 99.7% of the total process. Or
So wait, when you say 6 sigma, so for example, it's the total variation.
yeah, right.
The total variation from either direction from the total variation from the central tendency from either variation. So for example, if you had your the normal distribution was from -4 to from -4 to +4, then you would have 8 sigma, correct?
Absolutely.
Okay.
Right. So within 6 sigma, you will at least capture 99.73% of the total data, right? Only the things will go out of this 6 sigma that we have plotted. Right now, there are 2 factors. One is your specification limit given by the customer. This is the lower one, and this is the upper one, right?
I'm sorry. Hold on 1 second. Let me. I want to ask that question again. The 6 sigma that you mentioned, it is because I just want. I'm sorry if I'm asking you again. It is because it's from -3 to +3. That total distribution it totals to 6, correct?
Right.
That's why. Okay, it's not because your lower specification level and your upper specification level is -6 and 6.
Now it is nothing to do with that.
Okay, okay,
This is the total spread we are looking at, right?
okay. So okay.
Now the specification limit right now on this particular graph is showing towards -6, right? And the upper
Yeah,
specification is showing us 6. It could be even 1 or 2 also. It could be anywhere. That's given by
yeah,
the, right? And
yes,
if you look at this particular graph, a process is very ideal, right? It is well within the specification limit, and it is
yeah,
very close to the centrally aligned, right, average,
yes,
which means this process looks very ideal.
yes,
Now we'll have to go back and check, is that really true, right? So for example,
yes.
if I look at another distribution, look at this one, right? The first one, your LSL is here, your USL is here, and this is the average, right?
Yes.
Now you have this particular area which is going below the LSL, and this particular area above USL.
Yes.
That the process is not capable. We have this many defective area.
Yeah.
Right? And in this case, and the average is right in the middle, which is good. In this case, this is a little better. You have this defective area and your target is somewhere here, which means
Right.
it has gone off the target. And this is the ideal situation where it is well within LSN and USL, and it also is right on the target. Your average is met. So there are two metrics. One is reducing this particular variation, and this could be improving the average, which we can close to this one. Right? So three different ways in which a process can perform.
Right. So you want to be on target and you want to be within your specification limits.
Right.
Yeah.
Okay. Now, over a period of time, a shift that happens to any process. The average could today be 10 days to process something. For over a 6 months period of time, there is a shift that will happen from the average to either for a better reason or move towards the USL, or it could move towards the LSL, right? For obvious reason, there are multiple changes, technology introduction or standardization, anything that can happen, right? And there's a shift that happens, right? So there are two things that we measure. One is short-term sigma and the long-term sigma. We will go through the difference in some time.
Okay. Hello?
Yeah.
Okay, I'm sorry.
Yeah. Okay. All right. So here are three different processes like we saw. The first one is a better process. Second one, everything has the same average, right? And a person who is only looking at average, for example, as a measure.
Yeah, but the dark green one is the best one because your distribution is more reduced and you're right on target, you know?
Right. So let's say a business metric going out to the leadership, right? And people report out average on how the processes are performing. These are three different processes. Based on the average numbers, everyone would think everything's going fine, right? And this, we will identify what is the actual variation in the process, even though the targets are met.
Right. Right. They would think that, yeah, the target is met, but on those three processes, they all met the target as far as being in the central tendency. They were all within the parameters, but one of the targets was the dark green was really on target, and the other green, the peak was on target, but it had a little bit of distribution towards both the lower and upper specification limits.
Right. Absolutely. And let's say different lots to understand the long term and short term how it works. Right. You have lot 1 plotted here, lot 2 here. So this is a time series chart, right? And you have distribution starting from here. So the first lot, let's say it is divided into 3 months each. The first 3 months, your data points was somewhere here above the average. And the second quarter, for example, it's come down here. And the third quarter came here. Fourth quarter is reflected here. And Q1 of the next year, very similar to the first lot 1, right? The distribution was here. And this is the long term. So if you are studying data only during the Q1 of current year, right, you will have a certain shape of the data and you will get a specific median or average that you're looking at. However, you take this Q2, you will get a different kind of reading. So it's very important for us to look at long-term sigma, how it performs, and then drill down to the short-term sigma. Is that clear?
No. Oh, okay, never mind. I see the center tendency now, and I see the lower and upper specification limits. So, okay.
Right.
Okay.
This could be affected by special cost variations as well, like we explained before. Some of the quarters you'll have peak orders coming in, where it's difficult for you to meet the target. And few months, beginning of the year, probably it's not a peak, it's not affected by season. So end of the day, if you measure sigma or process capability over a period of time for 1 year, it will be totally different from only measure the Q1. So there's something called short-term sigma, short-term capability, and there's long-term capability. There's always,
absolutely.
always a shift, right? That happens.
Yeah, absolutely. In the long-term study, usually it's reviewed, with all the metrics from, if it's on-time delivery, it would be from supply chain. It'll be reviewed from like the annual business review from a top level.
Right. So it's very important for us to understand the shape of the data and the period at which we are going to collect the data and start analyzing. Right? We do not want to pick up anything which is at a peak quarter. We do not want, because that's special cost, a special time in the year which we don't want to take that as the benchmark to analyze and come up with our solution. We'll probably look at an average or study the long-term sigma, take out the shift from there, or reduce the outliers or remove the outliers, and a data which can be measured. That's why we study the shape of the data.
Yeah, we in my experience, we review it monthly. And from a kind of higher level or departmental level, we review it monthly. I have my team, my leaders do weekly reviews to see the tendencies, and then and then we do our reports monthly from a department, and then from a site level, we review it every month, and then departmental is every month, and then from a site level, manufacturing site level, we do it quarterly to see the tendency, if are we meeting our targets or no, but we see the trends. And then of course at the end of the year, we collect all the data and define it, and we see the trends. Did we meet our target or not?
Right. So that's from the operations standpoint. We look at different kind of reports, different timely reports, etc. from project standpoint, when you look at it, my objective is I'm here to tackle a problem. I'm here to find solution to a problem, right? So before I go ahead and collect my data, or after I collect the data, I want to ensure I'm studying the right data. Did I pick the right period at which I have to study, right? So that's what happens when I study the shape of the data. Right? So this is an example again in a different way. Yeah, so this is another pictorial representation of how they've done it. So this is the long-term distribution. Your target is, or your central tendency is right here. And for your sub period, it's all over the place. Now, let me show you how I study the shape of the data using Minitab.
Using what?
Minitab.
Okay.
All right. Now what you see here is a data, right? You have different airlines A, B, C, which are my X's, one of the variables. And you have the dates, total complaints received, people boarded, and the complaint percentage. Right. So this is my Y. Let's say I'm trying to reduce the complaint percentage for an airline company or across different airlines. Right. Now, first part, when I check the shape of the data, I want to check if it's a normally distributed or it's not a normal distribution, non-normal distribution or not. So one of the tests that I do, go to stat, basic stats, go to something called normality test. Okay. It is also called Anderson-Darling test. So I select the complaint percentage, click OK. I get a distribution chart like this. So what it does is, across this axis, my data is plotted, all the complaint percentage, right? And I have the probability value of p value right here. It is 0.933. So if my probability value is above 0.05, which means that my data is normal, which is, it is on a normal distribution. Did you get that?
Yeah. So basically, you're saying that if it's 99.05% accurate, you have normal distribution.
Right. So if it is above 0.05, it is considered as a normal distribution.
So is that axis was it generated? Is that like an average?
In this case, it is straight away taken each of the values, right? Especially if you have bigger data, for example, it will average out. So there's a backend calculation that happens. How big?
That's what I'm saying. Yeah, like there has to be like an average from all those complaint percentages, which
right.
or from all of that data, and then it generated the axis, right?
That's right.
Okay, and then where you have all the data plot points, you can see the deviation from the. You can call that axis, or you could call it central tendency.
Central tendency, right?
Okay.
Okay, and a couple of other tests that you can use. One is that you can do a graphical summary, complaint percentage. You take it, you get this. Here again, you have a normality test p-value, which is the same. And you also get to see the distribution of the data, right? And you know what the mean and standard deviation for this. And you get the first quartile value or median value, third quartile. So there are multiple things that you can, multiple tests that you can use to study your data. But this is a key point. We understand that this is a normal distribution.
Because it's 93.3%.
Yeah, so it's a probability value. It says, yeah, anything which is above 0.05, which means that 95%, it is probable that the distribution is normal. Probability of the distribution is normal.
Okay.
That's the confidence level that this data is in a normal distribution. If, for example, these three graph bars were here, right? So which means skewed towards one area, this could have given us a different result. Okay. So the key factor is, once we understand the shape of the data, when we proceed with further analysis, we'll have further test that needs to be done, or further study or further variables that we'll probably have to collect in order for us to complete the analyze phase. That's something we will learn forward. So just understand for now whether the data is normal or not normal. Okay. And we can also look at different variables. For example, if I put this on a box plot, say I take this with different groups, and first one is obviously the percentage. This one I take the airline. Right now, this is a distribution on a box plot. So distribution would probably start from here, right? And it ends like this. So this is a central tendency for airline A, and you have for airline B, and for airline C. So now I have one X, which is airline as an X, and their subvariables is airline A, airline B, and airline C. Now see, there is a difference in the complaint percentage average against each of these airlines, which means that there's a higher complaint percentage for airline B. So I need to really focus on airline B. That's what this particular graph says. And now if I look at the spread, for example, this point, which is the 25th quartile or percentile to the 75th percentile, the variation is quite high. First two airlines have a higher variance than the third one. Right, so this is how we read box plot. You can also get.
I don't understand what. I don't get it.
Okay, let me just tell you that. Now, if you see, what I did is, let me start from beginning. So now this particular data, right, there are two things. One is complaint percentage, which is Y, which is the problem we are trying to tackle, right? We're trying to reduce the complaint percentage. And now I have different X's in different columns. Let this be one of the critical X that we are trying to see. There is airline A, airline B, and airline C, right? We want to understand the complaint percentage, is it different between airlines or not, right? So we are putting it on a box plot. I go to start a graph. I select the box plot. I select with groups. I'm selecting the second option because I have different variables. There are three variables that I have. So I select in the graph variable, I select complaint percentage, which is my Y, or which is the problem that I am trying to address. And I am analyzing it against different airlines, which is airline A, B, and C. Right? And I get this chart. Now, what this particular box plot does is, it takes each of the variable, for example, airline A, and it plots against a distribution. Now, you don't see a distribution here. So if I draw it from this point to this point, that's the distribution, right? So the total variation is from this end to this end. And central tendency is what it is showing here, right? For example, if you look at it, the median of this is 0.07. And in this case, the median is 0.08, which is 8%. Right? Third case, the median is 0.78, which is 7.8%. Now it clearly says that airline B has a marginal or higher complaint percentage than
Okay, I understand.
B.
I understand.
Right?
Yeah, I understand. I do this in Excel all the time. I just didn't thought I didn't see how you did it from the beginning. But yeah, I understand. Just you're comparing three variables of three airlines. You're grabbing the percentage, uh, the complaint percentage for each one, and you're measuring it. And the size of the blue box is determined by the volume or people boarded or complaints.
Complaint percentage, right?
Complaints. Yeah, I got it.
Right, and I'll also get to see the deviation or variation from for each line separately. So I know there's a trouble with airline B because there's a bigger variation than the rest of the two.
Yeah, the variation is that your median is like 8.25%. Yeah, 8.24%. And so airline B has greater, yes, they have greater amount of complaints, and they're also the percentage is higher. You know, there's a percentage is higher because it's complaints divided by people boarded.
Right.
And you get your percentage, and then you compare it with the other airlines. Okay.
Right, and also the standard deviation. The deviation is also quite high because for each day, few days probably your complaint percentage is low, and some days it's high. So there's a gap that I need to bridge to find out why there is a variation, right?
Yeah.
Okay. So this is on a continuous scale because we are collecting it in percentage, for example, right? Let me look at a different tool that we can use for a different kind of a data. I'm sure you're aware about this one. Okay, now this is a different set of data, right? This is a discrete data. If you look at it, it's showing the volume. Let's say this is the defect numbers for a particular service that we are providing. Let's say in Active Directory, we have 74 errors. In messaging, we have 53 errors. In the Office, there are 49 errors, just an example, right? I want to find out where do we have the maximum trouble, right? Which are the areas that we'll have to address. And this is a tool that we quite often use in business through Excel, which is nothing but a Pareto chart. Now, this is the 80-20 rule that we apply, right? 80% of the defect is caused by the first 20% of the total defects.
What? I'm sorry, repeat that?
Yeah, so what it has done is it is plotted. Let me give you another example. This is not.
Oh, what'd you say about the 80-20 rule?
Just give me one moment. I'm going to put a different number here.
Okay.
Say defects. Okay. So now I've given a different set of data here. If you could see. Now, let's say my on-time delivery issue is caused by, let's say about 3 plus 3, 7 factors, right? That's my XSR. And I find suppliers are contributing to 90 defects out of total. And sourcing team is contributing to about 50 defects. And planning team is 40, logistics 30, tech, different readings, right? So what I do is I take this data and put it in a Pareto chart, right? And the first bar, for example, is supplier. And second one is sourcing. Then you have planning, logistics, right? And then another line going here, which is nothing but the cumulative numbers plotted, right? So if let's say when it reaches 80, for example, here, right? This is the 80 percentage. So what it says is 80% of my total problem is caused by just 3 of the 3 out of 7 factors, which means if you apply the 80-20 rule, 80% of the problem might be caused by only 20% of the total X's that you have, which means that I don't have to break my head in fixing all these issues. First, focus only on the first 3 factors, which will take care of 80% of my total problem.
Right.
Right. So that's what the Pareto chart says. So very similar to what we looked at Boxplot. That's on a continuous scale. We identified who are the key X's that will be contributing to the problem. When I have a discrete measure, for example, to take care of, I put it in a Pareto chart to see which one is contributing more trouble.
I do these charts, but I don't use this type of chart.
Okay.
So yes, I understand. I understand it. The chart that I use is to do this type of analysis is. So I have all this data, and instead of creating your supplier, sourcing, planning, logistics, tech, operator, sales, all these columns, I grab the total amount, so I don't have that line graph, you know, that looks like it totals to be like 100. That would be my upper specification limit in one bar graph. So I would have one bar graph, and within that bar graph, I would have all these 6 bars inside that one bar. And it would show, so for example, supplier would be 90, then it would show sourcing right above it, 50, then planning, so on and so forth, but it would be one bar. So that right there, so the line and the 6, yep, all that, which total looks to be like 100.
This is a cumulative number.
Yeah. So the cumulative number would be, so you see the first bar, the supplier bar?
Okay.
That would be 100. That upper limit would be
40.
Right now.
You have to refer to this axis. So, yeah, sorry, 90, right?
Yeah, 90. So that would be
in terms of number, but in terms of percentage, it's 40.
Yeah, I know.
So when it comes to 80%, it's right
no,
here.
Okay. Okay.
So in real scenario, if you do a pivot on all your on-time delivery misses, you might have not just 7 factors, you might have 100. For example, if you do by business unit, you might have 10, 20 business units, right? And be breaking your head thinking, should I really talk to all the business heads of each unit and start fixing my issues?
No. What I do this. This is what I do. I just used to do. I just compile the data in a different chart, different type of chart. But this is what I do. And then after this, I view what's my what we call here in the U.S. my bread and butter. Like let's say 80-20 rule. I see what's my biggest factors that is contributing to my problem, and then I address it accordingly. But yeah, I do the chart, but I just do a different type of chart. But just essentially, it's the same data. I was just looking at this chart.
Right. Now, one catch to this. This is a very straightforward way of saying who's contributing to my issues. But in statistics, what we do is the next level of analysis, probably we'll do that in the next session, just to give you a brief. What we do is we do a study, we do a hypothesis testing to find out whether what we see is really true or not, right? It just says, of course, the total contribution. When you look at the total count of contribution, the first 3 is contributing to the maximum problem. But I really have to take a guess, saying that this is what it is contributing. But in reality, it may not be right. This X may not be statistically significant because the total volume processed by supplier could be much higher than what is processed by sourcing, right? So based on the total percentage of contribution, this number might be a fair number, right? Then what it means is the problem is lying somewhere else.
No, I understand it. No, I understand it 100%.
Right. So that is something we will see in the next stage of analyze phase.
Okay.
Right. So just wanted
This
to.
is good. This
So
is good.
Boxplot is something you've learned now. Pareto is something you could use. Right.
Yeah, yeah, for sure. It's good.
Right. And then I'll give you another tool that will teach you the stability for a period of time. Let me take a look at it. Okay. So here is another data. Just okay. I have another data which says minutes. Right. Let's say this is the cycle time of a process, right? Or the average call handling time of a process, for example. So you'll see 12.65 minutes, 14.94, 12.79, and it's a huge data set, right? And I want to check, and this data is collected over a period of time, let's say for a year. I want to see if this data is stable or not. So what I do is go to start, quality tools, and I check the run chart. This can be done on a time series also. So I select minutes, and then subgroup size, let me assume just one for now. Click OK. Now this is what I get. And this is called a run chart. Right? In the same way, so this is a central tendency, let's say, so close to 13, right? And your data is spread above and below the central point in different distribution. So across different subgrouping that Minitab has already calculated. So it is distributed. Now there are 4 factors I look at. One is clustering, mixture, trend, and oscillation. Clustering is nothing but if you have too many data points just clustering around one particular area. If that happens, my p-value would be less than 0.05. Currently it is above 0.05, which means I don't have a clustering issue, right? A mixture, clustering in one area, clustering in another area, and different areas, then it's called as a mixture. And trend is something going upwards during one particular time. It could be because of a natural or there's a peak issue like we discussed earlier, or there's a rainy season or a snow season where your data would show on the peak. It will show us a trend. Then I have a problem with trend. Then oscillation is nothing but going up and down in a very consistent basis. Then I have an oscillation problem. So if any of these values are below 0.05, then I have a problem with stability on this particular data. So which means then I'll have to go back and see if there is a trend which it's an outlier which I have to remove. If there's a clustering, then I have to remove that area of data. Then I can study a much more stable data for further analysis. That's some alteration that I can do before I do the analysis. Is that clear, Ronald? Any question?
Sure. Okay.
So that's run chart. So you've learned normality chart to check the shape of the distribution. Run chart you can use for checking the stability of the distribution, right? And you can use Boxplot and Pareto depending on continuous or discrete scale. You can use that for identifying key axis and key variable that might be contributing to the actual problem. Do you want to take a quick break and then?
Okay, sure. Take a 5-minute break.
Okay, 10 minutes. I will get back.
Okay.
Is that okay?
Sounds good. Yeah.
Perfect. Thank you. Okay.
Okay.
Now we're clear with the shape of the data, the distribution of the data. Now we are going to assess the current process capability in terms of statistics. We already know from practical point of view where are we performing, because we have the lower specification limit and upper specification limit, and we know the average and we know the standard deviation. We know at what percentage are we performing. Right now, I want to convert that into a measure statistically, so that I measure something called capability, right? Which is mentioned here, CP or PP. The difference between CP and PP is nothing but short-term and long-term capability. So you can just look at one measure for now. Let's say CP would be the difference between LSL minus USL divided by 6 standard deviation, right? And that's the formula. And there's something called CPK or PPK. Here, the key difference is we look at the closest spec or specification limit minus X bar. X bar is nothing but the sample mean, the average mean of the distribution, divided by 3 times the standard deviation. Now that's a formula to identify 2 key factors. One is CP, and the second one is CPK. The key difference is the first one will tell you whether your process is capable and within the specification limit given by the customer or not. That's it. The second one gives you a little more information whether your target is, or are you hitting the average or not, right? So which is why the factor of X bar comes into picture. I'll give you an example and show you the difference. Now here you have the LSL as well as the USL, right? And your central tendency is somewhere here. And for this particular distribution, CP value that you've got is 2. And CPK value you've got is again 2, right? So any value which is 1 and above means that your process is capable. And I will show you how that calculation is done. And for CP as well as CPK, if any of these capability number that you get is equal to 1 or above, which means that your process is capable, right? Or second point is it is well within the specification limit. Case, this process again is within this specification limit. However, the CPK number is 1 and the CP number is 2, right? And there's a difference. So if you are measuring only capability, the first part, I assume the process is capable, which is true to some extent. However, the average is way above the central tendency of the distribution. So this is what the CPK will help you to identify whether my process is doing well within the specification limit, as well as it is close to the average or the median. The third case, similarly, it has gone out of USL, which is why your CPK value is 0, even though the CP value is 2. Last case, it's completely off the grid. The CP is still showing as 2, and your CPK is -1, which is why it is very important for us to look at the CPK value instead of CP value. Now let me go back to the slide. Now let's look at the same data, right? And we'll try and calculate the capability of this process. Sorry about that, Ron. One moment.
Yeah, it's okay.
Okay. It's 5 a.m. here, 5:21. Okay. Okay, so now I have a set of data and it's calculated in minutes. And I want to check if my process is capable or not and what's my capability value. I go to stat, quality tools. And there's something called capability analysis. And then you have different categories here, right? You have one calculation for normal and one for non-normal. So the first thing we need to check the normality of the data. So let me just go back and do the normality test. I select the variable. What does this indicate?
It's if the normal distribution is valid or not. So anything above 5% is good. So anything above 0.05 is good. It
It's
means that
0.05. It's not 0.5. It is 0.05.
I'm sorry. 0.05. I'm sorry.
Right. Absolutely.
Yeah.
So it means that this data is normal, right?
Yeah, it tells you it's normal.
Okay, so now I can go ahead and do the test for normal distribution. Capability analysis, I check the normal. I select minutes, subgroups, keep it as 1 for now. Let's say my lower specification limit is 10 and specification limit is 13, which is my call handling time. For example, I'm taking a call should be minimum 10 minutes, and maximum should be 13 as a customer. And I'm going to calculate. Now I get this chart. Right. Now the distribution is like this. Now there are few values that you want to look at. You have the sample mean. The standard deviation is also given here. Now I want to look at my CP value, which is 0.53. So what earlier I mentioned, anything which is equal to 1 and above would be a good process, which means that the process is capable of meeting the expectation of the customer. And it's clear from the graph itself, a lot of things which is going beyond the upper specification limit, right? I've mentioned it as 14 and then 13, and there are a lot of data points which is taking more than 13. So which is why my CP is 0.53 and my CPK is again further low, which is 0.08. And this would be my base measure to determine what is my performance right now as a process. And it can also give you a little more insight on the parts per million defects, right? Million opportunities. This would be the total number of defects that you might have, which is why it's giving you that kind of a CP number. And if you have to manually calculate without the help of Minitab, you will end up doing all this. You first come up with the Z value, which is X minus X bar. Basically, you come up with the average mean deviation from each of the values versus your central tendency value. And then you come up with the Z value. And then you look up to the table. Against that Z value, what would be your number? And that will determine what level of sigma that you're at. Right? And if there is a short-term sigma of 3 sigma, for example, that you're getting with a DPM of 1350 per million opportunity, your process performing at 3 sigma. And if you're calculating a long-term sigma, like we mentioned earlier, there will be a shift, and a standard industry standard of 1.5 would be reduced from the sigma capability of short-term process, right? So for example, if you're currently at 3 sigma as a short-term sigma, your long-term capability would be just 1.5 sigma. Any questions here? It's all basically how it calculates in Minitab backend which you don't really have to worry too much about.
Okay.
If we are using the tool, I think that should be good enough for a green belt level project. Right. So key things that you understand is, one is your capability number. What is your current sigma that you're performing it for your process? And what's the DPU, or defect per unit, or defect per million opportunities? So basically you're getting a baseline, where to start from. This is where my process is. I want to take from 3 sigma to a 4 sigma process, or I set a target of 2 to 3. So I'm setting up a statistical target for myself, or I'm analyzing my process into a statistical problem. Now I know where I stand, right? So once I start improving my process after the analysis, you first always measure the capability of the process post improvement to see if there is a significant improvement that has happened. And the main objective of converting it into a sigma number is it will become much more easier to compare between different kind of processes. For example, you are managing a supply chain business, right? I am working on a call center business. How do I compare these two businesses in terms of something metric? Because you will be measuring on-time delivery, and mine is totally different, an average call handling thing. How sigma helps is we convert both into a number which is common, right? The capability of an on-time delivery versus the capability of average call handling can be converted into a sigma value, and it can be compared. So tomorrow, if it is the same person who's managing both the business, can say, okay, both my processes are performing at the same level, or one is at a level and the other one is at a different level.
Well, that's why you take it. That's why you calculate the per million opportunities.
Right. That's why I calculate the Z-score, which is CP, CPK, and then arrive at a sigma level of my process.
Okay. Total number of defects divided by total number of units produced. You get a percentage. You get a number. Let's say by 20. Divided by number of opportunities for error, 1 unit. Okay.
Any questions there? Good?
No, it's okay.
Okay. Now you don't have to think too much about it. If you're doing a project at a green belt level, there's always a black belt who can help you out running these reports. But the thing is, it's very important on how do you solve a problem, right?
Right.
The methodology and how do we solve an issue. So first we define a problem, probably starting from the customer VOC, right? And then you converting the VOC, which is in a very high level English, you convert that into a critical to quality metric, and you finalize on one key metric that you want to drive, which might improve your customer satisfaction. You take that metric and you go ahead and build a business case saying, why do I have to improve this particular metric? What is the key objective and what kind of impact it can have? How much money would this save for me? Then I create a further detail on the problem statement. I clearly define from what period to what period I experienced this issue and what is the quantity or what is the current metric of that problem. Then I look at identifying key members who can help me in driving this project, right? I identify people who can collect the data for us, who can support us in terms of business, who can give us the go ahead or the sign off. So you include all these people into your team, right? Then you go ahead and make a data collection plan. Before you build a data collection plan, you have to ensure your measurement system is accurate. Then you do a measurement system analysis, right? And you minimize or reduce the variation which comes from the measurement system analysis so that the data remains with maximum process variation or a product variation. And then you take that data and you check the shape of the data, whether it is normal or is it stable over a period of time. And based on that, you conduct your analysis. You plot that on a box plot or a Pareto to identify which are the key axes that might be contributing to my issue, right? And also you measure the capability of process in a sigma term, so that all the metrics which can be converted into one number, which can be used across industries, across different processes, to make people understand which is your statistical measure of your current problem, right? And that's where you are right now. And the next step would be benchmarking your capability, right? Any questions?
Okay.
In
Nope.
terms of the story, the
No,
flow?
everything's fine.
So from Greenbelt standpoint, you don't really need to get into details of statistical calculation. The key thing is when you have a problem, right, at your process end, you put a framework to it and try and solve. And how do you solve is what a Greenbelt level project can help you with.
Okay.
Okay, excellent. So the next topic is benchmark. So can you give me some examples on in your business, right? If you are trying to fix a problem, right? How do you come up with a benchmark? I mean, what are the methods you generally use to come up with the benchmark?
Well, it depends. It's very circumstantial, but I mean, a benchmark could be driven by customer requirements, So we'll have some problems, and we would put our benchmark and our targets based on the requirements from our customer. So we'll try to put some kind of timeline and in accordance to our customer requirements and demands, and then we'll put action plans in place to see if we can meet this target.
Right. Okay. So in very simple words, what we try to do is in a benchmark, we first look for any similar process which is performing better, right? If you are looking at improving an on-time delivery of a particular plant in your business, which is performing, let's say, below 80%, you go ahead and see, are there any other plants within the company which is performing about 90%, right? Which can be a good benchmark. You can always go and compare it against that process and see, of course, if they are able to do 95%, I can always, reach that target, right? That's one benchmarking. Of course, there will be challenges in terms of investment or technology or anything, but that can be a start.
Well, yeah, you could do comparisons like if it's from like a site level, something like that, like on-time delivery. You can compare your uh, current metric versus your sister sites or the industry norms to see what's the benchmarks that are used in the industry, or what are the benchmarks within your organization, but at different sites, and try to come up with an average and see, okay, what is gonna, or get the highest benchmark for that site that reflects similarities within your manufacturing site, and set it as a benchmark. But of course, those circumstantial, let's say the on-time delivery, perhaps my manufacturing site, I may have different problems that causes me to have, let's say, a very low on-time delivery. Perhaps I might be in a geographical area where there's a lot of, let's say, political disruptions, and that causes people to flee left and right, and therefore I have a low labor force. I don't have too much to choose from as far as labor personnel for labor force. So I have a lot of unskilled personnel, so which they cannot perform the job functions properly. Therefore, it impacts me and my operation. So my metrics will probably be lower than others and in more stable countries. So yeah, just to give you an example, so my benchmark wouldn't be as high as, let's say, my sister site that's in a country where it's very stable and has a high labor force, high output and educated labor force or skilled labor force.
Right. Absolutely. So no, you get an idea. So what we do is, if we get a comparable process, we take that process and we do a capability analysis like we did, right? And we get a sigma level, and we keep that as the benchmark for us to improve. Or we, if it's an industry benchmark that we are using, we obviously take that as the target for us to meet in terms of sigma. Or it could be given by the customer saying that we need to improve to this stage. They might be talking to us in a metric standpoint, but we will again convert that into a sigma and see that can be used as a benchmark. But always keep it realistic so that we do not end up not completing the project by not meeting the but benchmark is of course a reference. Your target was always set at the beginning during the define phase. Okay. Now, you remember this slide, right? This is the fishbone analysis. This is where we get into right?
I can see it. I can see it.
Identify different X's. For example, this.
I cannot see it.
You can see it? Awesome.
No. Okay.
Okay. So this is a cause and effect diagram or fishbone analysis that I was talking about earlier. So the central axis, which would determine our Y, or the metric that we are trying to improve. In this case, high wait time for cars and idle time for technicians, which is the Y we are trying to address. And then you divide that into 3 or 4 different buckets, which is the key axis that which can be key nature of things that will be contributing to that problem. And then you start brainstorming, right? This is something we do before measure, and we come up with multiple X's which might be contributing to the issue. For example, if on-time delivery is your Y, supplier could be one of your X, right? Supplier A, supplier B, supplier C might all be performing at different levels. And planning organization could be an issue. You might have a planning organization which plans A-class parts, might be doing much better than the one parts which comes from the B class, because their planning efficiency is much higher. I'm just assuming. So you put planning as another X. Logistics, for example, you might be using 3 or 4 different logistic partners to run the business, right? And you can assume that could also be an issue. So these kind of inputs come from the SMEs, right? And based on that, we start collecting the data, right? One example is earlier we saw one of the airline plotted. So on this data, right, compliant percentage is the Y that we were trying to target. And one of the X is the airline company. Right? There are different airlines A, B, C. So similarly, the data points actually increases. You'll have multiple X's that comes here. Now, as part of analysis, what we have to do is 2 things. One is identifying which are the X's that has a direct impact on Y. Is that impact statistically significant or not? Right? And the first part we already solved, which means we used a Boxplot or Pareto to identify which are the key X's that is directly related to Y. right? And the second part, we need to find out whether these are statistically significant or not, these contributions, right? That is something we do in hypothesis testing. That is the next phase of analysis that we will be conducting. In hypothesis testing, what we do is there are two types of hypothesis. One is null hypothesis and the alternate hypothesis. Have you used this technique anywhere, or have you read through it somewhere?
Which one?
Hypothesis testing?
No, we don't. I don't currently.
Okay. Just to give you an example, just one moment. So in this scenario, if you see, right, there are four blocks. You have, for any scenario, there might be two correct decisions, right? So we don't know the decision initially. So what we do is we make an assumption, right? And we assume in the first case that there are two factors that we are looking at, right? We are saying there is a difference between A and B, right? My assumption is there is a difference. In actual, if there is a difference, then my null hypothesis is accepted, right? And the alternate hypothesis gets rejected. Right? Did you get that?
Okay, not different. True, different. It's false. Correct. Not different. Not different. Different. Okay.
So for example, I'm assuming an X, which is airline, right? I have airline A, B, and C. I'm assuming there is no difference, or it is not making any significant impact on Y. That's my assumption, right? Then I conduct the test statistically to prove it yes or no, right? And if my answer is yes, for example, there's no difference between there's no impact from the airlines to the Y, the call handling time, then my null hypothesis is accepted. My alternate hypothesis is rejected, right? So that's the basic. So in here, how it works is in this scenario. I'll just show you. Here I get p-value of 0.08, which means that it's telling me there is no difference between student 1 and 2 against each of these subject. Both are performing at similar level, even though the marks look extremely different. Let's say for English, it's 55 and 83. Maths, it's 65 and 70. Biology, 75 and 80. In statistically, what it's saying is that's not a significant difference to come to a conclusion saying that it is not due to a subject they're having different marks. There's some other issue with this particular student. Okay, now this is the list of service that we have, right? And there is volume. Let's imagine this is a defects. Okay, now I'm trying to find out any of these categories are significantly impacting my Y or not, which means that should I really go and do any kind of research to actually start fixing issues between these categories to improve my Y, right? Or will I be wasting my time? That's my question. So I go and do a hypothesis testing, which is used for discrete analysis, which is called chi-square test. So I click on the chi-square test. I select my defects. I select my service. So what I'm trying to do is I'm trying to compare the the defects versus the service, right? Click on OK. So this is the Pareto that we did earlier. Here it clearly sees the first 3 bars is a top contributor, right? And we can always come to a conclusion. Yes, of course, there is a significant impact this particular X has towards Y, and we should start working on, right? Now I am trying to prove this, right? So then I do my chi-square test and I look at my results. Now my p-value is below 0.05. So when it is below 0.05, what it suggests me is that my alternate hypothesis is accepted, which means that there is a significant difference in the expected count versus the Y, which means that these are real contributors to the problem, right? So this is a very significant X for me. So I can keep it as an area of study. I can go ahead and look at these 3 factors and see what is causing the defect. I can go and study the rest of the 80% and see what is helping them or what is working well there. And I can start improving the first 3 factors, which will definitely give a good improvement on Y for me. And that's how I do the hypothesis test. Did you get the point, or is it confusing?
Yeah, sure.
All right. So similarly, for each category, there is different tests that we perform. But the key point would be, if you have about, during our fishbone analysis, right? We came up with, let's say, about 20 X's, right? And in the 20X, we have to finalize, right? We don't really have the time to go ahead and research on all the 20 X's to drive improvements on the projects. So through hypothesis testing, what we do is we find out critical X's, right? Out of 20, maybe only 6 or 7 would be directly impacting Y. We can ignore the rest. And how do we do that? We do that through hypothesis testing. So that we get a final list of X's, which is really creating a significant impact, and then we focus only on that. That's what we do in a hypothesis testing.
That's similar to the Pareto chart, and you can apply the 80-20 rule, kind of, no?
Pareto gives you a count. It gives you a cumulative check. But what hypothesis testing does is, right, it also calculates the proportionate contribution, right? Just to give you an example, you see this screen, Pareto?
Yeah.
Okay. Now here it's very clear that the first 3 is contributing, right? But what hypothesis, the chi-square test does is, it calculates the contribution from each of these, right? Maybe the first one, right, first category, it has more number of defects because the total volume on this particular would be proportionately equal to the rest. You understand what I'm saying? Let's say if it has 340 defects, right? These 340 defects might be causing from 1,000 units, which is processed under this category, right? In the same way, you have, which is about 35%, right? Same way, the second one is giving me 144 defects, which might have come from 500 units processed by the second one. If you look at it, the proportion is equal, right? When the proportion is equal, then it's not the X which is creating issue, it's something else. So this particular test calculates that proportion and puts an expected count, right? And if that proportion is kind of equal, then my null hypothesis is accepted, saying that it is not really significantly contributing to the Y. So even if I'm spending time there, I'm just wasting my time. So you don't just go by Pareto alone. You always go ahead and see whether this is true or not.
Okay.
Did that make sense? Or
Okay.
would you mind repeating that point? I just wanted to make, because it's very critical when we do the analysis.
So, I mean, you say that it impacts it. So the X value will have a, let's say, for example, defects. It'll have a number of defects, but you have a bunch of different you have a bunch of different X values, right? A lot of variables in the X line. And each one has a certain amount of defects or whatnot. But what are you dividing it by? What are you multiplying it by? You're saying it's proportional.
Yeah, your voice is breaking. So what I understand is, see, okay, let me try another Pareto. Maybe I'll be able to explain this better.
No, I understand the Pareto. That's
This is great. Yeah.
You go back. I mean, the other chart, the chart.
Mm-hmm.
Okay, so you can generate the other chart. I understand Pareto. It's fine.
Yeah, I understand.
The share square. But see that p-value, it should be greater than 0.05 to see if you have normal distribution, right?
Yeah, if it is above 0.05, then this does not have any significant impact. If it is above 0.05, if it is less than 0.05, of course, this X has an impact on Y, which we need to further take it forward and see what's happening.
Oh, okay.
Right?
Okay, that's why when you generate the chart, all the X's, all the variables in the X value, well, at least the first three, they were pretty significant. Where do you get those values from?
I'm just putting some random number.
Okay.
Um,
So what you're telling me here is that total count 1,000, you had 90 defects. Okay.
okay, so now I have total count is 1,000, right? In that 90 are defects.
Mhm.
500 total against sourcing, and that 50 are defects. Out of 240 are defects. Logistic. Yeah, so I'm not getting that. So what I was trying to explain to you is I plot against each of these variables the defects and the non-defects, right? And then do a chi-square test. So how chi-square test calculates is against this 1,000 defects, non-defects, right? You have 90 defects. Against 500 non-defects, there is 50 defects. Similarly, against 50, there is 40. Now, if you look at, there is a proportional difference, right? So for supplier, there is a less proportionate defects compared to the planning, even though the number is higher for supplier.
Yeah.
Right. So what it says is, it's not the number, it's a proportion. Right? So it can be statistically significant or non-significant. Right? Planning out of 50, 40 are defects, which means there's a huge problem here. Right? Here, out of 1,000, they are only making 90 defects by supplier. Even though in Pareto, it will show me as supplier is the highest defective case. But if you actually look at it, planning is the one which is causing the problem.
Right.
Through Pareto alone, you will not be able to come to a conclusion. You should always check the proportionate kind of a test which chi-square or hypothesis does, and that will tell you whether this X is really significant or not. Otherwise, you can just ignore. You don't have to go just by number.
Yeah, but in this case, this table here, this data table, you can just get a percentage you get the defects divided by non-defects, get a percentage, put that up, plot that in a graph, and you can see which X variable is the most impactful.
Right. Yeah.
So your focus is your X variable, not the Y variable.
Right. Absolutely.
Or yeah, your Y data point. Yeah.
So if I get about 20 X's in total, I can, you know, in the fishbone analysis, people came up with 20 different X's through different brainstorming, right? And I'm confused whether to go ahead and spend time in all of those 20. Then I first put it in a Pareto box plot, and then I do a hypothesis testing to check, is this really significant or not? Then select only the one which is significant. Just ignore the rest for now, because that will have a bigger impact on your Y. And you will sooner, you know, you will meet your target faster than if you're working on all of them.
Yeah. Yeah.
Okay, so this is some, you know, representation of what test is required for each kind of data to do the hypothesis testing. For example, if it's a continuous and variable Y, right, then you can just get it from a histogram. For an attribute data, it's a Pareto chart, right? If you have more than one column, right, which means you have a continuous Y and discrete AX, for example, right, then you go for a box plot, continuous Y. So you go for a box plot and one t-test instead of the chi-square that I was doing, right? And that's something you will see here, right? You have one sample t-test, two sample t-tests. So based on the kind of data that you have, you end up choosing different tests that you should be performing.
Okay. Okay.
Okay, so that's just some information that you should keep in mind.
Okay.
Now, any questions so far from?
No, it's fine.
To go. So now we've learned from 12-step point of view, we've learned establishing process capability, and then how do we define performance objective. That is something we just learned on how we will probably look at an identical process and do a calculation of that process capability. That we will keep as a benchmark, or we'll go for a customer given benchmark or an industry given benchmark. And the 6th point was to identify variation sources from all the X's that was identified using a fishbone analysis. We will first do a box plot Pareto to see who's contributing, which X is contributing more. And just to prove whether this is significant or not, we go ahead and do a hypothesis test and only prioritize the one which is critical. And that's where we are with the story in terms of analysis.
Right.
So in the next 2 sessions, what we will do is improve. We will do it probably in the next, whenever it's scheduled. We will screen potential causes. We will take out all these X's. We will screen all those potential causes. We will do a design of experiment. Again, further, root cause analysis to identify what could be the issues against each of those X's. And we will come up with solution, right? The solution can come from various methods. That's something, again, we will discuss. And then we will set tolerance level and do a pilot solution, right? Once we have the solutions in place, after we get the approval from the necessary authority, we will go ahead and put some, we'll run a pilot for a month, and then we'll take the result. And based on that, we will set a control limit. And we will again do a 1-month test, and then we will check if the processes are within control. And that's how we close, improve, and control. But we will see the techniques that is used for both in detail during the next session.